Flux, in particular electric flux, is roughly speaking field times area. So our first version of the formula would be flux is E times A, and that would be electric flux. Later you'll learn magnetic flux as well. So electric field times area. What area? Well, if you have an electric field, say, pointing in the positive x direction, Ex is 100 newtons per coulomb, which is the same thing as 100 volts per meter. And perpendicular to it, you had a rectangle that was, say, 3 meters wide and 4 meters tall. That area would be 12 square meters, and your electric flux pointing through this surface would be 1200 volt times meter when you multiply those units. So that's an example of electric flux through a flat surface. If it were at an angle, suppose the surface was on the floor and the electric field made a 20-degree angle with the perpendicular. In that case, the electric flux would actually be EA cosine theta. The electric flux is actually a dot product. It's a dot product of the electric field vector and what we call an area vector. The area vector is perpendicular to an area, sticks straight out of it, and the magnitude is equal to the area. It turns out having a vector perpendicular is the easiest way to describe which way a surface is oriented. You use the perpendicular vector because we're good at vectors. Describing a plane in 3D, and say, well, it passes through this point, and this point. There's all kinds of complicated ways to do it, but the simplest way is just say which way the vector sticking out of it points. Now, there's some ambiguity, so you could say the area vector points this way or this way, and you have to define it. But if your surface is a complete enclosure, if you have a closed surface, like a Gaussian surface, then outward is defined to be positive. So, if we had a cube with that same electric field, we would have 6 faces. Now the electric field would be sticking straight out on this side. It would be going straight in on that side. Along the top it'd be sort of skimming along, and on the front it'd be skimming along, and on the bottom it'd be skimming along, and in the back it'd be skimming along. Now, inward vectors, like this one, count as negative flux, and outward vectors count as positive. But what about these vectors that are skimming along the surface? Well, if the area vector's like this and the electric field's like this, that's a 90-degree angle, and the cosine of 90 is 0. You don't have any field vectors sticking out of that or going in, so it's neither making positive nor negative flux, so it's got to be 0 flux. So if these were these 6 faces, the electric flux would be, if they all have the same area, EA, you'd have positive EA for the right side, and 0, and 0, and 0, and 0 for the top and bottom and front and back, and negative EA for that side, and you would end up with 0. In a uniform electric field, the flux through a Gaussian surface is 0. That tells you that there's no charge present, because charge changes the electric field. If you encounter a charge, the field is different. So if your electric field is not changing, there must not be any charge there. And the reason we study flux, Gauss's law says that the electric flux through a closed surface is equal to the charge inside divided by epsilon naught. Gauss's law is a great way to avoid calculus. So if they want to have you do fancy calculations, but they can't make you do calculus, then they bring in Gauss's law. It only works without calculus in some nice symmetric situations. So pretty much the only situations you're ever going to have to deal with are what I call flat and round. So the round have spherical symmetry, and the flat are infinite sheets of charge that are parallel to each other. Plus, you know how to add fields. There's one other situation where you could use it, and that would be if you had a long charged wire or a cylindrical tube. So something that has cylindrical symmetry, basically edge on it looks like a circle. You need a lot of symmetry, either flat plane, line, or point charge, or uniform ball. Those are the only situations you can deal with. So we can run through some examples of those. Let's say that you have a ball of charge, and you have a constant, or no calculus here, so it better be constant charge density. Remember, rho stands for Q divided by volume. So this is not a conductor. If it was a conductor, all the charge would run out to the surface because it's all repelling and trying to get away from each other. But this would have to be some insulating material that has charge all through it. And in fact, you need some kind of force holding it together, or otherwise it would explode because all the pieces would be repelling each other. So assuming it's strong enough to hold itself together, and you've managed to embed charge all the way through it, what does Gauss's law tell us here? We need symmetry. We have symmetry, it's round, so our Gaussian surface had better be symmetrical as well. If you have a sphere, then your Gaussian surface should be around it. Oh, just as a warm-up, how much charge does this entire ball have? The charge here is the density times the volume. And if the volume, if it's a sphere, we have 4/3 pi r cubed, where big R is the radius of the ball. And little r is going to be whatever distance we happen to be at. So if I draw this Gaussian surface with a distance little r, I can ask how much charge is inside that? So the Q inside would be rho times 4/3 pi little r cubed. So not all the charge is inside that ball because it's such a small ball. This Gaussian surface is only enclosing part of our ball of charge. All right, but what does that tell us about the electric field? Gauss's law says that the electric flux is equal to the Q inside over epsilon naught, but this has to be a closed surface. So a sphere is a closed surface, so that works. And we have to center it because we can't do it in calculus, so things have to be a lot of constant things. You can't have too many things changing at once, or you need calculus. So everywhere along here, the electric field has the exact same strength by symmetry, and it's all pointing outward, which means the electric flux boils down to just E times area. So we have E times the area. Now for this Gaussian surface, the surface area of a sphere is 4 pi r squared, and this is little r. So E times 4 pi little r squared is equal to the charge inside over epsilon naught. Now since the charge inside is rho 4/3 pi r cubed over epsilon naught, and that equals 4 pi r squared E, we can determine E, the electric field. Rho 4/3 pi r cubed over 4 pi epsilon naught r squared. So r cubed and r squared mostly cancel, leaving an r. The pi cancels out, the 4 cancels out, and we end up with an electric field of rho r over 3 epsilon naught. That is the electric field at a distance small r from the center of the charged ball. So if little r is 0, that means we don't have any electric field. Which makes sense, because which way would it point? It's right in the middle. There's no preferred direction. So it's got to be the 0 vector. As you get further and further out, your Gaussian surface encompassing more and more charge, so the electric field is actually building up linearly until you get to the surface. Now what happens when you're past the surface? When you're past the surface, the math changes because some of these little r's become big r's. If we are out here, we still have E times 4 pi little r squared, because that's our Gaussian surface, but now little r is greater than big R. But the Q inside, the charge only goes out to big R. Like this is the grand total charge. You don't get any more than that. So that means the charge inside would be rho 4/3 pi big R cubed. And then we could divide by 4 pi little r squared. Okay, we have electric field times area of the outer Gaussian surface. We end up with a similar formula, except it's dropping off as r squared. So if you had to graph this, if you had to graph electric field versus radius, the electric field would grow linearly until you got to big R, and then it would become the inverse square law we're used to for point charges. So that would be a description of the electric field inside and outside a ball of uniform charge density. Now let's examine a charged tube or solid cylinder. Let's say it's very long. so that we have that symmetry, has a radius r, length L, which is gigantic, and Q, which is gigantic. Now, if we are viewing it from far away, so it just looks like a line, it would have a linear charge density, just Q divided by L. If it's a conductor, and we zoom in on it close enough to see, then we would see that the charge is all on the surface, so it would actually be a sigma. Sigma charge divided by 2 pi r times L. There's even a third possibility. If this material was charged all the way through, it had a uniform charge density in 3D, then the charge density would be charge divided by the volume, which would be pi r squared times L. So which one it is depends on your problem, depends on the exact description. So let's look at this edge on so that we can see the symmetry that we're going to use. So out to radius r, let's say we're doing the third case. We have a charge density throughout the volume. Now this is not a sphere, this is edge on of a long cylinder. Now how are we going to draw a Gaussian surface? Right, and how do you pick a Gaussian surface anyway? We're trying to pick something from symmetry, right? Like our general idea is we want to find the electric field everywhere. So let's pick a random spot. Let's pick a spot on the outside of this, say. And I'll just go out a distance, I'll call it small r, and I want to know the electric field right here. Well, if this thing's positively charged, I certainly expect it to point outward. And the edge on view here might be like that. The electric field points straight out, and the distance is r. All right, so how am I going to build a surface? Now, it's important that we keep things as constant as possible. We would like a bunch of points that are all the same. In particular, where are all the points that should have the exact same field strength, even if not the same direction? And that would be every point at the exact same distance from the axis. Okay, well that's a lot of territory, because if you're talking about distance from the axis, you're talking about wrapping a cylinder around this. But Gauss's law requires a closed surface, so what are we going to do? We're going to need to put on end caps on this. And it's important how we do the end caps, because we don't want to make a mess. If we put like slanted end caps, then we're going to have like electric field pointing out in all sorts of crazy directions. It'd be difficult even with calculus. So we don't want to do that. So there's a clever way to do this. If we slice it exactly perpendicular, then the electric field is doing whatever complicated thing it's doing, but it's doing it in that plane. So even though it's got different directions and different strengths, depending how far out you are, it's all flat. It's all skimming along the surface, so it's making no flux. There's no flux through the two end caps in this situation. And so that's what makes it a good surface. So we're making a cylinder. Our Gaussian surface is going to have an area 2 pi little r around times length long. And that is essentially the area of the side. And the area of a cap would be pi r squared, but that's going to make no flux, which means that our electric flux coming out of this surface is going to be electric field times 2 pi r times L. And that flux is going to equal the charge inside. Well, it depends how they gave it. If they gave us the rho, then we need the total charge. Well, that total charge is going to be rho times pi r squared L equals Q. And that's a big R because that's the radius of this thing. So the charge inside is rho pi big R squared L over epsilon naught. So if we divide, the L cancels, good news. Pi cancels. And we get an electric field. Divide by 2r, and we get rho r squared over 2 epsilon naught r. So that would be one way of describing the electric field outside. But what if we're on the inside? What if we're only like part way out? Then we can do like in the sphere example. We need a smaller Gaussian surface. It's going to be the exact same shape, it's just going to be embedded in here. And the only difference there is we're going to have a different total amount of charge. It's going to be density times the enclosed volume. The charge in there would be rho pi little r squared big L. So if we do our same math again with electric field times 2 pi little r times L, because that's the area, equals the charge inside over epsilon naught. Now we get r's canceling. We get L cancels out. We get 1r canceling out. We get pi canceling out. And we get an electric field equal to rho r over 2 epsilon naught. That looks kind of eerily similar to the sphere one. It's just we have a 2 instead of a 3. Because instead of sort of growing in 3 dimensions, we're growing in 2 dimensions. So we have the charge density, and the electric field is growing linearly with r again. If I graph the electric field, it's going to grow linearly until we reach r, and then it's going to drop off gently as 1 over r, because this is a 1 over r decay, not 1 over r squared as it would be for a point charge or a ball. So that's another example of Gauss's law.